So In-N-Out is absolute garbage. The Dairy Queen is where it's at. Everybody knows that. So here we are looking at stuff. We're going to start a new section today. Now my hope, I don't know that it's going to make you guys talk any more than normal if the desks are here or not. My hope is that it doesn't make you talk more like as I'm going through stuff, because all I've done is taken 3 feet and made it 1 foot. So it's really not that big of a difference. But let's check out the lesson. We get to start, or continue rather, talking about quadrilaterals. And the other day we saw that quadrilateral is just a fancy name for a what gon? A four-gon. So we've looked at two so far. One of them is a trapezoid, and there's a bunch of stuff about trapezoids, right? If they're isosceles, there's some nice things that come out of them. And the other shape we looked at was a kite. Now we named them all, so like you may be getting them like mixed up in your head. Today we are going to talk about a larger class. Kites are pretty specific, sorry. Trapezoids are pretty specific. In today's lesson 6.3, that's supposed to be a couple days, but we'll see if it really takes a couple days. Our focus, instead of on kites and trapezoids, we get to look at, and we're going to define here as our first little start, parallelograms. Parallelograms. Now, we're going to get a bunch of theorems out of this. And today, the cool part about it is you all love proof like a ton. And I can tell it. Everybody emails me all weekend saying they want more. And you get your chance to practice today. And proof's hard for how many of you guys? Fair. They should be challenging. How do you get better at something? You just got to practice it. That's what it really comes down to. Now, as we're going through this, I care way more about your like actually writing the proof or the logic to prove something. Care way more about the logic. The other side of it's nice, but let's define this first. What is a parallelogram? 15, 20 seconds, chat with your neighbors. I want your layperson definitions. 20 seconds, go. What's a parallelogram? What do you think of parallelogram? I'm not giving you a hint, I'm just thinking. Nope, I'm just moving. How many sides, first of all? Mm-hmm. Don't feel stupid, that's not the right thing. 4. What do you think has to be true about opposite sides? All right, so we're going to define this, and you guys have had 15 or 20 seconds. I did not give us a countdown. Real quick, if we're talking about a parallelogram, how many sides? So we'll just say it is a four-gon. Now, there's a real word, and what is the real word there? Quadrilateral, not square. It could be a square. Quadrilateral is the right one. A four-gon with, what do we need to be true if it's a parallelogram? Two sets of parallel sides. So you mean like, is there a better way we can say that? Every side. If the top is like this, what side is it parallel to? The bottom. And the left side is parallel to the right side. So we could just say a four-gon with opposite sides parallel. Instead of trying to say with two, like you are right, there's two pairs of sides that are parallel. I'm just going to shorten with opposite sides parallel. Sonny, what size letter are you using?
No, I have plenty, but it just doesn't want to pump out.
Okay, so I'll give you a pencil here in a second. Now, opposite sides parallel. What's the shorthand for parallel?
2 lines.
2 lines. Now, just so you know, because you're going to see it, parallelograms, I will probably write it every time, but I say that and I will forget. What does this mean? Parallel. And if I do this, what do you think I'm writing? That is a parallelogram. That is how I write it. It looks like the word logram. It's not. It's this. So a four-gon with opposite sides parallel. Now, I'm going to sketch a parallelogram here, and we're going to work out some theorems using the same picture over and over. Okay, so check it out. If I want to draw a parallelogram, our first topic today, since we're looking at these and we have it defined, is let's work out some properties. And we're going to look at properties of these guys. So we're going to work these out. They're going to come in the form of theorems here in a second, but let's see if we can't reason any of them out just initially. I'm going to draw my first parallelogram. Now, I'm going to try to make it not look like a rhombus, because a rhombus could be a parallelogram. I'm going to try to stretch it out and make it look like a tilted rectangle. And I'm doing this very intentionally. And let's check here. Liam is missing. I need to do attendance. What are we going to name this one? So I heard like 4 different things. You can give me a real name. We'll just write it. John. Here is, oh, Liam's gone today. Okay. Here we go. Bottom left is Lima. Top left is India. Top right is Alpha. And the bottom right is Mike. All right. Now, if I want this to be a parallelogram, right now, is it? Is it? Isn't it? So if you don't want to assume, what marks had I better put on this thing? Arrows. Now, help me out here real quick. We are missing Liam. Anybody else? Sophia. Liam and Sophia. Wasn't Liam here this morning? Oh. That's... I am so nosy and I want to ask questions, but it's none of my business. We'll talk later because I have like 5 questions for you. Okay. That has to be parallel to that. How do I mark the other side? I can't just use 1 arrow. 2 arrows. Look at us getting crazy. Okay. All right. So, as we're going through stuff, is that working now for you, Sonny? Do you need a... Okay. All right. As we're looking at it, we have a couple different ways we can go. I'm going to make some claims, and we can do this a couple ways. We're going to work out some properties of parts of these. Do you want me to say, here's the theorem? I want you to prove it. Or do you want me to ask a question and say, what do you think is true about this? Or we can mix and match as well. You'd rather say, what is true about this? Okay, so a couple things. This one's just silly, but all of these theorems are going to start with a parallelogram, and we're starting with parallelogram Liam. Now, if I wanted to write triangle ABC, and I just write this, don't write this down, but did I really just write triangle ABC? No, what do I have to put in front of it? A triangle. What do you think we're going to put in front of a parallelogram? A parallelogram. So, for all of these next few theorems, and let me see how many we're going to get. I think we get 3 theorems right here. So let me double check that just in case I'm wrong. We get first is theorem 6, 7, and then 8 and 9. Yeah, right? So we are going to consider for the next 3 theorems. Next 3 theorems use, and I will copy and paste this, but we're just getting practice with notation, parallelogram Liam. Okay. Now, what? It is. Okay. So, here we go. For this is a weird one, but whether you want it in scratch work or not, I'm not going to give you the names of the theorems yet. What happened there? Nope, we're not doing that. Disregard. Don't know why all my trig stuff just turned on. Who said cosine? How do you know it's cosine? Whoever said it. Okay. Oh, it's so easy. It's so easy, but we'll get there. Yep, so most of you have probably never seen it. Maybe a little bit, maybe. Anyway, here's what I want you to do. First one, this is going to be theorem 6.7, but we're going to work it out here. I'm going to use the pink stuff here. Here's what I want you to think of. If I give you this parallelogram, and this is a wonky one, but we're going to try it with this first one, and if we have to change the order, we will. I have this lovely parallelogram. Copy, and we'll paste it here. Undo that. Cool. So if I give you this parallelogram, and I just recopied it so we can draw on it, I want to know, what do you think happens if I want to compare opposite angles? So if I said, what do you think is true of I and M? Any gut feeling? They are opposite from each other. I agree with that. They might be congruent. So maybe we have some intuition here. I'm going to give us a different one first. I want you to tell me what you think about is true between Li and Am. This side and this side. Now, here's my bigger challenge for it. They are parallel. That is not where I want to wind up, just so you know. I think there's a bigger relationship to it. Anybody have the gut feeling on what we might say about those? They are parallel. Anything else? Anybody else think they might be congruent? Okay, gut feeling, maybe. Even if you don't have a gut feeling, I'm going to make a claim, and we're just going to switch this the other way, because just discovering it, and sorry that I kind of made it feel like we had a choice, but we don't really. We're going to define the theorem, and then I'm going to let you guys try to prove it, because the immediate part is pretty, like, you guys all came up with it right away. So here we go. Theorem 6, 7. Okay, check it out. Next three theorems, we're using parallelogram LIAM, which means I don't have to say given a parallelogram anymore. Okay, we're going to make a claim, and I want us to try to prove it. The opposite sides are congruent. Here's my challenge for you, and it's going to bug me. Is it clear that we're using this, if it's a parallelogram, then the opposite sides? It feels clunky in mine, but okay. My goal for you is I'm going to give you, I don't know, 3 minutes. I want logically to see if we can come up with a justification. Convince me of this. And we'll do a quick proof underneath where I'm just going to add to this picture and stuff is what we'll do. Cool. I want you guys to think about it. You don't have to write the formal proof. I want logic to get there. 2 minutes. Convince me that Li and Am are the same. I'm going to give you a huge hint. I'm going to use this. I would add that diagonal. 2 minutes, I'm just looking for the logic. We'll do the formal proof together. How could we ensure that those are the same? Sorry. 3, 2, 1. What was the point of me adding this diagonal? So I do get 2 triangles. So let's work our way there. The first one that I see is with 2 triangles. If I'm trying to show that IL is the same as this and that AI is the same as ML, then if I could show these triangles were congruent to each other, that would suffice. That would work. That would be enough because I would just use corresponding parts. So now the goal becomes, how do I show these triangles are congruent to each other? Now, maybe, just maybe, we can do this pretty straightforward. I heard somebody else say theorem train or something like that. I'm going to pretend like this is not the chapter that we're in right now, and you won't erase yours, but if I erase this, does this look like something we talked about like months and months ago? We have 2 parallel lines, and they are being transversed by this. Well, if I have parallel lines and a transversal, what winds up being the same? There it is. So like if I have 1, 2, 3, and 4, which ones are the same? 1 and 3 are the same, and 4 and 2. Those are on alternate sides of this line. And are they between, on the interior, or outside? So they're interior and they're alternate sides of the line. So let's just look at this. What angles can I guarantee are the same right now? So you can't say L and A. So if I put my numbers back, is that 1 and 2 and 3 and 4? So if we add these to it, let's work in. A, how do we start a proof? Every proof. The given. And then I'm going to, before I even write that, because we don't have like exact statements, if I want to prove this theorem, what is it that I really need to show? So Li, that segment, had better be congruent to AM. Is there another pair of opposite sides? LM, I agree, should be congruent to what? IA, or LM and AI. The order doesn't matter if we're just writing a segment. That's what we're trying to actually show. If I give you a parallelogram, we should be able to show this. Now, right off the bat, we're just going to say parallelogram, and that's all my given, because we have this picture. So A, parallelogram. And the justification is it's given. Now, if I mark something here, like you guys told me, I'm going to mark these angles and these angles. The second I mark my picture, which I hope you all have a picture, but what do I need to do as soon as I write it here? We need to write it here and justify it. So just now, if you guys have all the same numbers, it's so much nicer than using all the angles. Angle 1 is congruent to what? Angle 1 is congruent to angle 3. And any others? Okay, so that part is all fine and dandy and awesome. It's perfect. Why? Love it. Alternate interior angles. Now I'm going to take my picture. I'm just going to move it down so that we don't lose it in the proof. And I'll retry that so that I can get it actually selected. So we'll do that and undo it. Okay. Now at this point, good thing is that we have angle as a shortcut, right? That's one of my 4 triangle shortcuts. It's not. Huh. Well, is there any of them that have angle in them? 2 angles. So we have angle, side. I'm just going to write these up here. Any others? They have 2 angles. Angle, side, congruence. Side, angle, side. That only has 1 angle. Angle, side, angle. I think I misheard you. Okay. It's one of these 2. It has to be. Well, okay, we need to decide which one. Are there any sides you can guarantee are the same? LA is congruent to itself. Why? Reflexive property. Love that I'm hearing it as reflexive instead of reflective, but there we are, reflexive. And now that I have these marked, what can I say about those 2 triangles with confidence? Weird. They are congruent. Now, on delta, let's see here. I don't care the way the first one spits out. Michelle, how would you name the first triangle? A triangle here that we're going to write the congruent statement for. ILA. ILA or ELA is congruent to which other one, Tristan? ILA. So careful. Now, if you're rusty with this, let's check. Am I wrong? ILA goes blank to 2, like 2 arcs to 1. How do we go blank to 2 to 1? M to A to L. And like, it's easy to make that mistake. And I think that I make it from time to time as well. Triangle MAL. How did I know those were congruent? Angle, side angle. I'm looking for one of those 4. Now that they are congruent, what can I tell you about like pieces? For example, IL is these 2, right? And that matches up with what? IL and MA. Hey, that's one of the things we're asked to show. So here, IL, based on this congruent statement, is congruent to MA. And now that I write this, I can say boom, and I have to use double dashes so that they work. Those are the same. Any other corresponding parts? AI and LM or ML, whichever order we go. And how did I know that that was true? Corresponding parts of congruent triangles are congruent, and look at that. Now, we are going to kind of skirt around this a little bit. Instead of us just using this and then getting examples with it and then writing another theorem, I think that maybe, just maybe, we can work out some other theorems here, since we already have this proof up. If I had elected, and I'm just going to talk a little bit, if I had elected instead to draw this diagonal, and you don't have to redraw it, it's just me thinking, could I have done like the same proof? And we still would have got congruent triangles, right? Now, we're going to skip a theorem, and the order is going to be wonky, but that's okay, because this is a natural place to think about it. Everybody okay with that first one? So if you ever get a parallelogram, instantly, not only do you know opposite sides are parallel, but now we also know they're what? They're congruent. You can mark them as congruent right away. Okay, beyond that, this next one, we're not going to prove it. We're just going to use it. and use the picture that we just worked out. It's going to be weird, but we're going to call this theorem 6.8. Just kidding, 6.9, and we'll hit 6.8 here in a minute. I know we skipped one. So let's see, this last one didn't have a name, so this one won't. What's our, sorry? Not really. Like, there's no names here. Most of the time I make them up. But these ones are just going to be, there's not even a point to name it. We'll just say opposite sides congruent is how we'll justify this one. This one, what do you think I can say is congruent to L? And sorry, A is up here, right? Why do you think those are congruent? Why would opposite angles be congruent? All we said was opposite sides were. Yeah, so check it out. We could use, and there's a bunch of different ways. To make this big angle, do you agree it's angle 3 plus 4? What makes this big angle? And 3 and 1 are the same, right? And 4, so these have to be the same. There's no other possibility. Now, eventually, when we got to this congruent statement, could we have just said angle L matches up with angle A? And just match it up there? We could have, right? We already did the triangles congruent, and that's exactly what this theorem tells us. Given a parallelogram, and just so we don't lose it, you don't have to write it because we already wrote it, but given parallelogram, and we'll just name it Liam because that's the one that we've been working with. And you do not have to write this because we already said given, because we already wrote this up here. I just don't want you to lose track of it. Give me that parallelogram, then opposite angles are congruent. And this will happen for every single parallelogram. Opposite angles are congruent. Which means if we're looking at Liam here, and I know we already have it, but you guys didn't have to draw it again, it means for the parallelogram that we drew, angle L is congruent to what angle again? Angle A. And I'm going to use this fancy and symbol here instead of my normal one. That's the up here, the logic one. And what is angle I congruent to? I is congruent to angle M. And we would prove this the exact same way. Just add the diagonal. If we see the triangles are congruent, then the angles must be congruent. Okay. Anything crazy happening yet? All right. There's one more that we need to dig into, but I'm not even going to draw the parallelogram. And I think we can work this theorem out. This was just a natural place. It's the same proof, just so you're aware. The last one. You do not have to draw this. I just want to dig way deep. Okay, we have that. Parallel lines. And we're going to cut them by transversal. We're doing a quick memory check. Don't just shout it out loud. Between you and your neighbor, I want you to, one of you, explain it and see if you can justify it. The other person just listens. And I want to see if you can get through the whole time them explaining it, and then ask follow-up questions or disagreements, but let them explain everything first. Deal? Do not interrupt your partner. I don't care who speaks first. You can do 1 out of 1, rock, paper, scissors. I want to know, what do these add up to? Don't shout it. Rock, paper, scissors. Whoever wins can pick whether they're describing or listening, but I want to know, what do those add up to and why? What do these add up to? Okay, harder question. Why? They're not corresponding. They are consecutive. If I were to take this angle, do we all agree that that and that are congruent? Why? And then this angle plus this angle add up to what? Why? Because they're a linear pair. And then that angle is the same as this one because of alternate interiors. So these two must add up to what? 180. Now, do you agree that this is just part of a parallelogram? So I don't think we really need to draw another picture. I'm going to change colors one last time just so we can see the difference in these theorems. Because all of these are just old theorems that we've already dealt with. We're just looking at them through a different context right now. So last one for today is theorem 6.8. And, excuse me, theorem 6.8, it tells us the following, and I want to make sure that we have them. If we have a parallelogram, so given a parallelogram, it's the same thing, and we'll just slightly change it. Given any parallelogram, and there's me logram, but remember that's parallelogram. And let's see how we want to word this. On this one, These are consecutive angles because they hit one after the other. Are they all inside of my parallelogram? Like these are inside and they're consecutive, right? Could I have done it from here to here and the next angle I hit was here instead? No matter where I do it, they're consecutive. The consecutive interior angles, we see they always add up to what? 180. Is there a word to say they always add up to something? To 180 specifically? So has to be 180. You're thinking on a different part, but if they always add up to 180, the word that we use is supplementary. Okay. So there's our theorem. We've already proven it. And if you didn't catch it, that little tiny bit when we were talking about what do these dots add up to is the proof. Like that's it. We've already proven this. We've used it. Parallelograms just happen to have this lovely relationship in them. Now, the cool part of where we're at is there's only one more theorem that we want. But here's what I think I want to do. Do any of your other teachers give you brain breaks? Do you ask, do you need them? I'm not going to change what I do, just so you know. Okay, so here's my first question. We do have a quick brain break because we have a bunch of vocab words that I'm dying to talk about. I have one student who I have not had a word that they didn't know what it means yet. I've never seen most of these words, which is awesome because I'm learning a lot with you guys. Two things. First, 30 seconds, I want you to discuss, why do I give you brain breaks? Like, what's the whole point of it? What do you think it is? For the next 3 minutes, we're going to sketch this theorem, and I want you guys tomorrow, without just looking in the text, like don't just cheat through it. I want to see if you can come with an intuitive idea of what this might say about it. Okay, the question for you, we're not going to write it as a theorem. Weird. Here's my question that I want you to think about tonight, and we're just going to put it as Q for question. Q? All right, check it out. What is special about the two diagonals of, and diags is short for diagonals, a parallelogram? Now, just to try to preemptively shut down one of the incorrect guesses, I'm going to draw a really obnoxious parallelogram. And I would not draw this one. I just want to really highlight it here for you guys. This is a parallelogram, and it looks dumb, but it is, right? Now, if I had drawn a normal one, the most common incorrect assumption, and I'll just draw a normal one here, but you don't have to. If I draw this like this and make it really nice and not look dumb, what do you think somebody might conclude about this diagonal and this one? They might decide that they're congruent because it kind of looks like it, right? This is a parallelogram. It looks like maybe they are. If we take this really obnoxious one, this length and this length, do they look as congruent anymore? Okay, so let me fix it again some more then. And this is just I'm not going to put the marks and stuff, just so you guys know. If I do this one, it's going to be even more clear. Is this still a parallelogram? I can mark it as such, right? It kind of looks like a kite as well, but it's a parallelogram. Is this diagonal, do you think, the same length as this one? So I can see there's a counterexample where it doesn't. So it's not that they're congruent, but they do interact. My question is, what does your gut say how they interact? My second thing is, anybody who has Sophia's number, please remind her that I post these videos on YouTube, and then remind her to smash that like button, subscribe, don't ring the bell.